Hello everyone! In this video we will continue to examine topic 5.2, the heating effect of electric currents, and in particular we will examine a multi-resistor circuit. In fact, those in parallel. So, just like the previous exercise with multiple resistors in series, I would encourage you to sort of pause the video right at the end of this little intro and solve out this circuit. As before, that means the following three things: calculate the equivalent resistance of the three resistors, calculate the potential difference in current for every resistor, and calculate the power generated in the battery and dissipated in each resistor. So I would encourage you to pause and fill out our table here. All right, so how do we do this? All right, first steps first. We fill in what we know. We know that resistor 1 is 4 ohms, resistor 2 is 3 ohms, and resistor 3 is 2 ohms. Okay, so 4, 3, and 2 for our different resistors. And we know that our total EMF is 12 volts. That's right here. Now, first steps first, we want to calculate the equivalent resistance of these resistors together. So we do that using our equivalent resistance formula. We add 1/4 plus 1/3 plus 1/2, and that gives us 13/12. Then we remember to invert this, which is a step often forgotten, because 13 over 12 is equal to 1 over the equivalent resistance, and that gives a resistance of about 0.92 ohms. Okay, and I've rounded that off. So once you have that equivalent resistance and you have the total potential difference, you can find the total current coming out of the battery and going back into it. And that value is delta V, 12 volts, divided by 0.92 is equal to 13 amps. Okay. So that gives us our current. Now the question is, how do we solve the rest of the circuit? Well, these are all resistors in parallel. And as resistors in parallel, we know that the potential difference across each resistor is equal to the potential difference across the battery, or the EMF. Therefore, these are all 12 volts. Then, once we have this column and these values, we can calculate the current in each of the individual resistors. So we know that V is equal to, or delta V is equal to I times R, and therefore the current is equal to delta V divided by R. So 12 divided by 2 is 6, 12 divided by 3 is 4, and 12 divided by 4 is 3 amps. So that gives us this full part of the grid. Then, to calculate each individual power, we can do it a number of different ways. We can use any of these three equations, but I'm going to use the potential difference across each element and the current through each element to do it. And so I'm going to find that 3 times 12 is 36, 4 times 12 is 48, and 6 times 12 is 72. That gives me, if we sum them up, a total power of 156 watts. Notice that 156 watts here is also equal to 13 times 12. So the power generated in the battery is exactly equal to the total power dissipated in each resistor. Take one more moment to compare the results of this particular circuit with the results of this one. Notice that the resistances are about the same. The EMF is even higher in the series circuit, but take a look at the final values. The total current is much lower, and the total power dissipated in each resistor is way lower. And if we take a look at this, at our parallel circuit, we can see that by wiring them in parallel, you are reducing the effective resistance of the circuit to below any of them individually, right? So the total resistance of this combination of resistors is 0.92 ohms. Okay, it's less than any of them because you are providing that current multiple paths to go in. Not only that, but then the total potential difference across each of them, and therefore the total current through each of them, is significantly bigger than in the series case, and that gives you a tremendous more amount of power delivered to each of these resistors. Okay, so pretty substantial difference here.